Okay, thank you very much, and thank you for the opportunity to present our work here today. And this is joint work with Erik and Peter Hansbo, Jönköping, Sweden, and Carl Larson, who is in Umeå, Sweden. So I'm going to follow this outline. I'll start with a kind of review of CAD finite elements and introduce the basic ideas where we use what we call weak stabilization, or could be called weak stabilization. That is adding some stabilizing form to the variation statement. And then we will look at some recent development where we use what we call strong stabilization. Here we instead do a kind of algebraic elimination of the unstable degrees of freedom. And then we go into hybridization and look at using hybridization to basically formulate a domain decomposition method. And then we apply hybridization and extend it to mixed dimensional problems. That's a situation where we have PDEs also on the interface between domains. And finally, we look at an application where we use hybridization for problems, surface PDEs on CAD surfaces with gaps. Okay, so very simple start here. You know, the idea in CAD finite elements or in unfitted finite elements is that you want to represent the domain in on a fixed background mesh. So we allow the boundary or the interface to actually cut through the background mesh in an arbitrary fashion. And then we get this situation here. We get some elements that have very small intersection with the domain, which can lead them to problems, of course. We can get stability problems, and we can also expect that we can get problems with a condition number for the algebraic system of equations. Okay, so let's look at how we approach this. We start with the domain and we embed it into a background mesh, and then we just mark all the elements that actually intersect the domain so that we get a cover of the domain. So this is the main idea for constructing a mesh. We have the background mesh and we have a geometric entity, and then we just mark all the elements that actually intersect that geometric entity. So it could be a domain, or it could be an interface, or a piece of an interface. And then we just restrict the finite element space to this active mesh. So to handle then the cut elements, these small cut elements, we add stabilization. So the basic idea in ghost penalty is that we add stabilization on all the faces which belong to an element that intersects the interface. And if we look at the formulas here, we have standard statement, here, cap AH, that bilinear form is the sum of AH and SH. AH is the usual Nietzsche form, and SH is the stabilizing form. So the stabilizing form, it can take different forms, but maybe the most common is this ghost penalty, phase-based ghost penalty term, where we basically get least squares control over jumps in normal derivatives across faces. And then we scale with an appropriate factor so that this whole thing scales the same way as AH. So this is the standard approach, which I think has been sort of dominating. And next here we will also discuss these algebraic techniques where we sort of look for a subspace. But first, let us look at the theoretical results that we have for standard CAD finite elements. Basically, the design of these methods is such that we can prove all the basic theoretical results which we have for standard meshed finite elements. So if we have the usual Nietzsche norm, but we append this stabilizing form here, we can prove coercivity and the continuity, and we also have an optimal order interpolation error estimate. And the idea here to construct this interpolation operator is that we take the function u on the domain, and then we extend it using a continuous extension operator, which is stable in different Sobolev norms. And then we just use a standard weak interpolant. So in this way, we can prove these estimates using standard techniques. And then basically the usual estimates follow, a priori error estimates of optimal order. And we can also show that if we stabilize, we have the expected optimal bound of the condition number, which could then, of course, be improved if we use some kind of preconditioning. Okay, so let me now discuss some recent work of ours on discrete extension operators as an alternative to weak stabilization. So again, we consider a domain, it's embedded, and we need to do something to handle the small elements. But here we take an approach more based on basis functions. So we think of a set of basis functions spanning the functions on this active mesh, and we decompose the finite element space into two pieces. One VHL, which is which is spanned by what we call the large basis functions, and then the complementing space VHS, where S is small and L is large. And VHS is spanned by the small basis functions. So these are basis functions that have a support with a small intersection with the domain. So basically we expect VHL to be stable and VHS to be unstable. And the idea is then to take these functions and extend them into VHS in such a way that we have stability and also optimal order approximation properties. So this, I think, is not a new idea. It's been around, I think, in many different contexts, in finite volume methods and so on. We did some work on discontinuous Galerkin with extension almost 10 years ago, in fact. And a little bit later, Santiago Badia and his co-workers developed these techniques for standard continuous Galerkin methods. So our approach is a little bit more abstract. So it generalizes to more general classes of spaces, including spline spaces and basically spaces that satisfy the Scherli definition of a finite element. Okay, so the idea is that we first divide the elements into two classes, small elements and large elements. So large elements, they satisfy this condition. So the measure of the intersection with T and the domain is larger than a constant gamma times the measure of T, and gamma is between 0 and 1. So gamma basically tells us how strict we are when we define large elements. So if gamma is 0, all elements are large. And if gamma is 1, basically it's only the elements inside the domain which are large. So then what we want to do is to associate each small element to a large element using a mapping SH. And this mapping SH is the general mapping. The only thing we assume of it is that we have this condition. So that is the distance between SHT and T should scale as the mesh size H. So it does not necessarily have to be a neighbor, but typically when you implement it, you look in the neighborhood, of course, corresponding to a small element, and you try to take this closest element, which is large. We can show that we can find such a map for a Lipschitz domain if the mesh size is sufficiently small. Okay, so here we can see the partition in large and small basis functions. And a large basis function, that's a basis function which contains a large element in its support. And then, of course, the small elements, they only contain small elements in their support. So this is for splines, this particular example, but it's the same kind of picture for finite elements. It's just these are C1 splines of second order, which means that they have support consisting of 3 by 3, a patch of 3 by 3 elements. So they have a wider support. Okay, so then the decomposition is given just by the span of these two sets of basis functions. Okay, so now we construct the extension operator. So it has two components, or two steps. The first is a preliminary extension operator, BH. And here we basically extend VHL onto a discontinuous space. So how do we define BHV? For an element which is large, it's just the identity. For an element which is small, we apply SHT and go into the domain, and then we restrict the function, okay? Which is now a polynomial here. So then we can canonically extend it outside of SHT, and we restrict to the element T. So for the large elements, it's the identity, but outside it changes. And this definition can then cause possible discontinuities. Then we apply an interpolation operator to push that function into VH. So we use a kind of weak interpolation operator of this form, where we chose these functional in a certain way to get good structure. Basically, we want this operator to be the identity on VHL, and that you can achieve if you choose these functionals here in the proper way. So to get then the extension operator, we just take the composition of BH and PH. And then the image of VL is precisely the extended finite element space. So this means that the dimension of this extended finite element space will be the same as the dimension for the extended finite element space. And we get these properties which I mentioned before. So if you just look at how to implement this, then we build the linear system of equations without any extension operator, and essentially we implement the matrix representation of the extension operator. And then we can set up a reduced system. So this matrix representation, of course, it will be rectangular. So we get a slightly smaller system here, which we solve, and then we expand into the standard basis again. So this is quite convenient as soon as you have built this operator, but of course it demands the implementation of this operator BH and also the implementation of the interpolation operator. So if we do this, we can say we understand that the sort of support of the basis functions, the extended basis functions, they have larger support. So here you can see an example. The purple here is a large basis function, and then it's extended to this pink domain here. So here you can see several different examples of how the extension sort of acts when it comes to the support. But it's important to realize that these support cannot grow. They're always limited. Okay, so using this framework, then one can, under sort of quite general circumstances, show that we have stability, and here omega h, well, that's the union here of all the elements. So it's actually a larger domain than the domain omega, which we have here. And we can also construct an extension, an interpolation operator for the extended space, and we have an optimal bound. We also have an equivalence between the L2 and the degree of freedom norm. So then, in the same way as before, we can apply this to our model problem, exactly the same formulation as earlier. And then let's just look very briefly how this works. If we know that we need this crucial inverse inequality for this normal gradient here. So in the first step, we just apply element-wise inverse inequality. We go up to full elements here, all the elements that intersect the boundary. This set here is a subset of omega h. And then finally, we use the stability here of the extension space. So here we don't need any stabilizing additional terms. We have built in this into the construction of the finite element space. And then we basically directly can apply standard analysis for Nietzsche's method and get all the results which we expect. So in summary, we can see that we get exactly the same results that we get for the stabilizing, for adding these ghost penalty and related terms. So let's look at a couple of examples. This is again these C1 quadratic splines, and here we look at the convergence for different gamma and its quadratic splines. So we have blue, that's gamma equals 0, so all elements are large, so we basically have done nothing. And then we gradually sort of increase gamma up to 0.99. And we can actually see here that this is the L2 norm and this is the energy norm. We can see that it's actually very insensitive to the parameter gamma, which is good. Here we can see that we have sort of shaky convergence. And we have to recall the fact that we can actually get convergence even if we don't stabilize. So we can get convergence even if the system is unstable. Just to see what happens with different P's, it behaves the expected way. And then the condition number finally here. If we have gamma equals 0, we do nothing, and then we have a huge condition number, and as soon as we increase gamma, and we eliminate these very unstable degrees of freedom, we get control over the condition number. We also see that we have the proper scaling, and we have a dependency on P. So this is quite general. In a mapped situation, we can also apply it by mapping back to the reference domain, and then we can do the extension in that setting, and we can push it forward. So here we have solved the problem on a surface, which is then obtained by mapping this reference domain. So we go here and we use the extension, and then we push it forward to the deformed domain. So one thing we're looking into here is sort of how to extend this now if this mapping doesn't have sort of full regularity everywhere. So it could be that it has lower regularity across certain interfaces, for instance. Then that will have a kind of effect on this theory. Okay, so some comments. We have done a lot of work over the years on these stabilizing terms, and now we investigate this approach as an alternative. We find that it's quite interesting to use it, and it seems to be actually quite competitive approach. And I think this has also been shown earlier by Santi Badia. It's important to notice that here, at least for these splines, we don't have strong dependency on this parameter gamma. It's very stable. And our numerical results validate the theoretical results. And then I want to point out that there is quite strong or close connection between strong and weak stabilization. And we investigate this in this last reference here, which is available on Archive. Basically, the idea is that if you construct your stabilization form properly, then you can actually let the penalty parameter tend to infinity and not cause any locking. But that doesn't work, of course, for the standard ghost penalty. You have to construct the penalty term in the proper way. And then actually, when you let the penalty parameter tend to infinity, you basically enforce certain constraints algebraically, so the limit is the extension. So this is quite interesting in that way that you can get the kind of, let's say, you can put these things into the same framework. I think that was kind of also really interesting, because we understood how to construct also stabilizing weak form in a better way. It's always good to have as little parameter dependency as possible. Okay, so that was that part, and then we go into the hybridized part. It's not as technical. It's more like a collection and an overview of how to apply these ideas to hybridization and problems with different domains. So a motivating problem for us is to look at porous media or materials with embedded structures. So we think of a material like this, for instance, where we have sort of three-dimensional domains, and they are connected by interfaces, and we can expect some physics both on the interfaces and in the actual domains. And typical approach here is that you actually resolve everything on a 3D mesh or a 2D mesh. So you represent also the interfaces using like a density representation. That's a common approach. So we don't want to do that. We want to sort of actually represent the geometry using different dimensional objects. So the idea is that if we look at the simple example here with 3 different domains and this interface here with a branch, is that we actually split it up into 3 two-dimensional domains and then 3 pieces for the interface. And then we apply exactly the idea we had from the beginning to construct our finite element spaces. We put it into a mesh and we mark all the active elements and we just restrict the finite element space. And then we get the space for that geometrical component. We do exactly the same thing for these interface components. We just mark all the elements that intersect the interface component, and then we restrict the finite element space to this mesh. So each geometrical component of the domain has its own finite element space, but all those finite element spaces, more or less, as in the basic setting, they are formed from the same finite element space, so they fit. We will look at some unfitted cases as well, but generally they fit, which simplifies computations. Okay, so basically we have our finite element spaces for each of the components, and we just sum them up or take the product of these spaces. And then we end up with this big finite element space VH, which in our special case here will consist of 3 spaces here and 3 spaces here. So it will be 6 spaces in total. Okay. Then to set up the to solve, let's say, an elliptic problem on this setting, we write it as a hybridized formulation. So we have the bulk problems here, and we have the flux continuity, normal flux continuity. And then we have this jump between the bulk variable and the hybrid variable, the interface variable. We demand that to be 0. Okay, and then we have some boundary conditions. Okay, so you see this jump here, u jump sub I, it's just ui, which is the bulk variable, minus the hybrid variable u0. Okay, and then we directly get this hybridized formulation, which looks pretty much like a Nietzsche method. It's just that now we have these jumps between the bulk variable and the hybrid variable here. And we can then, of course, do substructuring and eliminate the bulk variables. And this has also been proposed earlier in the context of fitted finite elements by Egger. So I'm just going to show you very quickly here that, of course, we have to stabilize each of these components. Okay, so we know that we need the bulk we stabilize using ghost penalty, for instance, or it could be the extension operator. The interface, here we stabilize on all internal interfaces, but we also need to add some kind of normal stabilization, because otherwise we'll have a lot of variation in the normal direction. So we need to add a little bit of stability here. So this is sort of the normal derivative in this direction to stabilize the problem. And then again, we can derive all the expected results in a very general setting. We can also prove a condition number estimate for the Schur complement. And here it takes this form. So it's 1 over h, which is the mesh size. And then we have 1 over the minimum of the diameter of these subdomains. So basically, if these subdomains are on the size of the mesh, then we get 1 over h squared. Otherwise, we get 1 over h. Okay, so let's look at a couple of examples to see the flexibility of this approach. So we look at basically two different situations. One is that we always use the global background grid to set up our finite element method, and we use the H method. The other setting is that if you want to couple sort of different spaces across the interface, then we can use a global polynomial on each of the components here. And if we do that, if we have a global polynomial on each of the components, then it's quite easy to do the transfer of information from one domain to the other, because this domain here, it never speaks to this one. It only speaks with that one through the hybrid variable. So if it's a global polynomial, then it's quite simple to do the computations. So this is the first situation where we have a fixed background mesh, and each of the components has its own active mesh, which we derive from that background mesh. Here is the situation that we have global polynomials, typically of higher order, for each of the components of the interface. And then we can actually use different kind of meshes in the different subdomains and facilitate the coupling using these global polynomials. So this is an example where we can see the standard approach. So this is the pressure, and this is the gradient, and here is the global polynomial approach. And obviously, if you have small details here in the solution, and then you will have to either use high order polynomials or some kind of refinement. You have to split this into different components, because otherwise you can't resolve that, of course, and we'll see that in a second. So let's look at the convergence study to see how that works. So here we have the standard approach. It's the energy norm and the L2 norm. And we get exactly as we expect for Q1, Q2, and Q3 optimal order. And if we then look at the situation where we have Q2 elements with the mesh parameter H for the bulk, but then we use global polynomials for each of the components for the interfaces. First, the blue, then we have Q2 in the bulk, and we have Q2 also on the interfaces. And then we see that we refine, and then, of course, the error in the interface will start dominating. If we then increase the order of these polynomials on the interfaces, then we get better results. So this is for Q4 on the interfaces. And finally, if we use Q6, we see that we can resolve this very well. So, I mean, if the solution is not too complicated or have too much small features, or you're interested perhaps in a, let's say, not super resolution of small details, then this approach seems to be quite interesting for model coupling. So this is another example for sort of showing what you can do. Here we have a kind of Voronoi partitioning, and we have an anisotropic material to the left, and here we have just variable coefficients to the right. So this is the solution with the anisotropic meshes, and you can see that all the meshes here, they are actually aligned with the anisotropic direction, and we do the coupling here between the subdomains using global polynomials. So this is the solution, and this is the gradient. And it's Q4 elements on the interfaces. And this is also an example here of different resolutions. So here we have a fine mesh, okay? this is a solution with a high resolution standard setting. Q2 elements for the hybrid variable and the bulk variable on the same mesh. Here you see that we have a very coarse mesh. So here the size of the elements is roughly on the size of the subdomains. Still capture the solution very well. And here we're actually using Q2 global elements on each of the components. So this is kind of like a hybridized version of polygonal discontinuous Galerkin. So you can see that when you have this framework set up, you can have a very flexible choice of your spaces, which is kind of interesting, I think. Okay, so let me just show now some applications here in the end, just to show what happens in a mixed dimensional problem. We typically add, now here when we did the domain decomposition based on hybridization, we didn't have any physics on the interface. Here we add in some physics on the interface. So this is an equation, an elliptic problem on the interface. So this would be like the Laplace-Beltrami operator. And in practice, when we use our three-dimensional elements, this is very easy to implement because these gradients here, they are just the standard three-dimensional gradients, but they are projected onto the tangent plane of gamma. And here we have sort of the inflow coming from the bulk variables. And we have kind of Robin-like condition between the bulk and the interface variable. So this problem can be generalized, and we have done quite a lot of studies. I will only show the simplest model here, but we have also derived models which can handle extreme variations in the size of the parameters and so on in a stable manner. So when you formulate a hybridized formulation, it actually ends up looking like this. So it's very simple in this situation. The only coupling term you have is this jump term. So it gets almost simpler than the domain decomposition formulation. Okay, so then the method looks the same way as with before, and of course we stabilize everything. So this is just a very simple example. I mean, it's a little bit hard to see, but here it's a crack here, and it bifurcates here. And now it's not active at all here, so here we sort of activate flow in this crack here, and you can see that it spreads up here. And here we activate the second branch here, and it affects the solution quite a bit. And finally, we activate the third. So this is a very simple example, but it shows that these interfaces, or the physics on the interfaces, often have a very large, they have a large impact on the overall solution. Because often they model flow in fractures, for instance, or isolating fractures. And therefore, we believe that this approach where you actually geometrically model the fractures is very interesting. I also think that this could be a good idea if you want to do like UQ analysis and you want to perhaps look at, let's say, Monte Carlo like simulations with probabilistic layouts of crack patterns and so on, which you could do in a good way, in a cheap way, I think, compared to using like a density approach. Okay, so finally, I'm going to apply this framework to this CAD problem. We have we think of a kind of complicated surface model. So CAD is a way of actually designing surfaces, and one can be interested in solving PDEs on these surfaces. So typical examples then could include wave propagation. Another one is shell theory for strength analysis. So such a model is built up by different patches. So you basically have a collection of patches that build up the model, and they each have their own maps to the reference domain, and then they have also an interface line. Okay, so that's the structure you have here. So it's kind of like a manifold structure, but it's not like smooth. Instead, you have these interfaces which connects your patches. And typically we will have trimmed elements here. So, you know, you will have different meshes on different sides and so on. But the problem which you often have in practice is that your model is imperfect. So typically you can have quite a lot of problems with a CAD model. It could be gaps, for instance, and that's what we're going to look at here. So you have a small delta gap between the patches. This could also be like positive or negative, so they can kind of intersect a little bit. But we assume that we know that these two boundaries, that they lie in, let's say, a kind of tubular neighborhood of distance of width delta. So another problem which I won't discuss now, but you can also have these singular mappings. So it's not uncommon that these mappings are singular. So that's also something we need to handle, but we're not going to look at that right now. So the idea we have now is to use hybridization. So if we look at a typical situation, you have a kind of part, a torus-like part here, and you have two different patches with a gap. So the idea is to actually use a hybrid variable, but we want to have this hybrid variable on a three-dimensional mesh, which covers this gap. And then to get information from one patch to the other, we'll transfer it using the hybrid variable. So now you can see that this is more or less exactly what we have done before. It's just kind of slightly different setting. So we form our spaces. We have our block mesh for the hybrid variable, and then our space associated with the block mesh. And then we have the two surface spaces. So typically these will be trimmed from left and right, and then they will talk with the hybrid space. And that's the reason we have these structured meshes here. This could also be an octree, of course. But since we have a kind of octree structure or structured mesh here, we can easily facilitate these geometrical computations, which we need to do. Okay, and then it's exactly the same formulation as before, but we have to be extra careful with this normal penalty, because it turns out that you have to design that in a certain way to handle the gap. Because if you have a gap and this guy is too weak, then you will get kind of discontinuity, because this is so weak. And that discontinuity does not occur if you don't have a gap. Then the reason you want to add stabilization in normal direction is basically for linear algebra. Here it's necessary because you have the gap. And then we add ghost penalty terms on all the faces in this block mesh. It turns out that you can analyze this And you can show that you want to take alpha to 2. So you get an h-2 scaling here. And this is also what the strongest you can have in principle without losing order of convergence. Okay. Yeah, so it's just a hybrid formulation with this block mesh, and then we use proper stabilization on the block mesh. So here you can see just the illustration in 2D, what happens when you use different stabilizations here in the normal direction. So if you have low stability, low stabilization, then you see that it gets unstable. If you have strong, what happens is that locks up everything. Because it's not, you get these additional couplings because of the curvature and so on. And here, if you have the proper stabilization, you get good results. So here, finally, we have an example. This is done then in Rhino, which is a common surface modeler. And you can see that you have these mapped elements, and we have trimmed elements across at all the interfaces here. Okay, so here we have the solution. So here you see the solution on the block mesh. And you see the block mesh, it covers all of the interface here. So this is a very robust way of dealing with sort of geometric computations. Instead of sort of looking at a map between these different surfaces and so on, we can do this in a quite rough way through this structured block mesh. And here you see the solution then on the actual surface. And when we have implemented this, it's actually all based on kind of, we work in a kind of basic Riemannian geometry setting with a metric tensor. So it's just a Laplace-Beltrami operator as it's expressed in Riemannian geometry. And I can also say that the analysis here is, the basic idea in the analysis is that you don't really do the analysis here on the physical domain. You pull everything back to the reference domain. Okay, and there you have your finite element space, your standard finite element spaces, and your interpolation bounds. So we basically formulate the a priori error estimates in terms of these pulled back functions over all the reference domains. Okay, so just a few very simple conclusions here. I think this extension approach is quite interesting. The reason we got into it from the first, in the beginning, it was actually that we wanted to do lumped mass matrices for explicit time stepping of wave equations. And that's not obvious how you can do that if you use a stabilized approach. So then we could actually show that you can lump for P1 elements if you do extension. You get a very fast method. We also establish sort of a close connection between weak and strong stabilization principles. The hybridized approach, I think, is very interesting due to its connection to geometric modeling and also to these mixed dimensional problems where you have different physics interacting on the interfaces and in the bulk and so on. And you can also have a situation where you actually allow a hierarchy of geometrical entities. So it could be like three-dimensional objects, it could be like embedded 2D surfaces, and it could be intersections between these surfaces, which you can handle using the same approach. So as long as the codimension difference between in the coupling is only one, this is kind of very automatic. You can handle very general situations. You can also do stabilized transport formulations in a very general setting. So that's kind of, I think, is a quite powerful way of thinking. And if you then couple it to these ideas, which I've explained with the choice of the finite element space and flexibility you get in such a situation, you get a very flexible system. So there are of course, this is not fully developed, but I think for linear problems, basic theory is very well understood now. So we are looking at nonlinear problems with more advanced physics close to the interface. So that could be like contacts with some physics going on at the interface, lubrication, for instance, or it could be expanding fractures coupled to poor elasticity in the bulk. So, and here it's of course very important to have formulations that can handle wide variety of let's say parameter values, because these parameters will depend on the solution in that situation. Another problem which I'm interested in is this being able to handle complicated patterns of fractures. It could be on different scales. So you can have a large scale fracture and you can have smaller scale and maybe do some kind of multi-scale formulation. So thank you very much.